Okay, here's part 2 on exponents and multiplication. So let's look at an example here. Let's say we had this. Negative 6 to the 4th power times negative 5 to the 4th power. So again, remembering the rules, if they have the same base, you keep the base. They don't have the same base. But they do have the same exponents, or the same power, so we're going to keep the power and multiply the base. So negative 6 times a negative 5. Remember, negative times a negative is positive, so that'll just be 30. And we need a better marker. We can't read that one. Okay, so that'll be 30. And then we'll just keep the base. There we go. Move that over. So remember, same exponents and different bases, you keep the exponents. You keep the powers, or the indexes, whatever you want to call them. Powers, index, exponents. If they're the same, you keep them, only if the bases are different. If the bases are the same, you keep the base. So the bases always overrule that. Okay, let's look at a geometry problem. Now, we know that to get the area of a rectangle or a square, it's length times width. Now, if it was a square, it'd just be side times side, it's the same thing. So we have to multiply this times this, and we'll get the area. So we have variables here. We don't have any constants. So it was saying x to the 3rd power times x to the 2nd power. That'll be the area. They have the same base, right? Same base, x. And in multiplication, we add the exponents, x to the 5th power. So since we don't know what the numbers are, the area here is x to the 5th power units squared. Seems kind of weird, but that's how you would write it. Okay, what about this? What if we had some constants, coefficients, which are constants, and variables? So the constants don't have any exponents on them, so you don't care about them, so you just multiply the constants. Negative 9 times 5. They're unlike signs, so you know it's going to be negative. It's going to be negative 45. So let's look at the bases now that have exponents, which is x. Same base. Right? And we add the exponents. Now, when you don't see an exponent, remember, it's not a 0. There's a 1 there. If it's invisible, there's always a 1. So that would be that answer. What if we had something with decimals? Same thing. So what do you think? What do you think this answer would be? Do they have the same base? Yes, same base. Keep the base. And by the way, you don't have to put the 0 there. You can just put 0.5 if you wish. They have the same base. So add the exponents. Negative 4. 0.5 to the negative 4th power. And by the way, this could be, which is 5/10. We know 5/10 is 1/2. So this is actually 1/2 to the negative 4th power. So when you see something like that, let's write it over here. Negative 4th, negative half, 1/2 to the negative 4th power. So what we're doing here is the same thing if we had negatives. With a integer, we always turn a negative fraction into a negative exponent into a fraction. So, for example, if I had 5 to the negative 4th power, well, we know it's 1/5. The base becomes the denominator, and we make the negative a positive in the denominator. So we're doing the same thing if we had a fraction. It's the same thing. It looks kind of weird. So we're saying 1 over 1/2 is a complex fraction here, and we always put parentheses around fractions to the 4th power. That's what that is. So if you see the negatives, remember, we always make fractions. And we can simplify this now. We can say it's 1 over 1/2 to the 4th power, so that's saying 1/2 times 1/2 times 1/2 times 1/2, which would be 1/16. So what this says is 1 divided by 1/16. Let me move this up a little. So we're saying 1 divided by 1/16, which equals 1 times 16 over 1. Remember, with division, we always turn it to multiplication and flip it. So this answer is just 16. So remember that when we have fractions with a negative exponent. So what about this? What if we have that? They have the same base, right? So we know we're keeping the base. They have variables for their exponents. So we can't add them, so we just simply say m plus g. That's it. So that's the answer. What about this one? Same base, right? 15, and we add the exponents. M plus 3. Or you can say 3 plus m. What if we had a fraction now? What if I took a fraction, and we put parentheses, and we made that a 2, and we made that a 3. Same base, 1/5. Add the exponents. Same thing. Okay, let's look at this one. Which one do you think has the greater value? Remember, whatever base has the bigger exponent, well, that's the greater value. So this is 5 to the 5th power. What is this? What is 5 times 5 to the 4th power? It's 5 to the 5th power, right? You keep the base, add the exponents. There's a 1 there, remember? 5 to the 5th. So this is equal. They're equal. Okay, last one. This one's a little tricky. Take your time, you can do it. We have variables as bases. So let's look at this. We have the C and the C are the same. So we can keep the C. There's a 1 on top of that C, remember. There's a 4 there, so that's C to the 5th power. We have an N and an N, so we keep the base. We have N, 5 plus 2, that's 7. And now we have an M. Negative 3 plus 1 will give us negative 2. And by the way, I'm just going to go a little further here, because we never want to keep a negative exponent. We always want to bring it down. So this would, since these are positive, we're going to keep them positive on top, but on the bottom, remember we're making a fraction here, so we're going to bring the m down because it was negative, and we would get something like this. So anytime you see a negative exponent, you know you make a fraction. But if you have it already with others that are positive, keep the positives on top, but bring the negative one down. And we'll go over more of that in another video. Okay, great job.